Don't you wish there was a better way? Don't you wish there was an even better way?
Our campus sits on 20,000 acres of foothills, but with foothills come steps. A regular cart won't do much for you on our hilly campus. You need a stair climbing trolley. Stair climbing dollies currently on the market cost anywhere from $40 to over $100 and are not adjustable. We wanted to build a stair climbing cart within a budget of $50 by reusing and recycling scrap material that was available to us in the shop. Our cart also had to have adjustable stair climbing wheels so that it could easily climb up stairs at different heights.
Before settling on our current design, we had one where the wheel radius was adjustable by way of a lever near the handle of the dolly. This design would have been effective, but it was complicated and would have been time-consuming and expensive to produce. We also considered a design where a stationary plate was connected to wires that adjusted the wheel radius as the wires moved up and down the wheel axle. However, the wires would not have produced enough force to move the wheels, and furthermore, we wanted an even more simple design where the mechanism moved in 2 dimensions.
Some of the tools we used consisted of a Beverly shear that we used to cut the sheet metal and to make the plates, followed by a drill press and center punches in order to drill the holes into the plates. Then we also used a mill to cut the holes and slots in the connecting rods, and a file and deburring tool following to clean up all the rough edges. We also used a MIG welder and angle grinder. We used the MIG welder to weld the bolts to the plates in order to make them more rigid, angle grinder to cut the bolts and to make everything smooth and prepped for welding.
Each of the 2 wheel assemblies will need the following items: 3 3/8 by 2.5 inch bolts with 3 nuts and 6 washers, 6 1/4 inch by 1 inch bolts with 6 washers and 6 nuts, 2 6 by 6 by 6 equilateral triangles cut out of 16 gauge steel, 0.7 inch pipe cut at 0.74 inches long, 3 1 by 0.5 by 8 inch hollow aluminum rectangular tubing, a cotter pin, clevis pin, and 3 6-inch wheels. The first step is to machine the 2 triangular plates and 3 pieces of the aluminum tubing per the specs in the drawings of SolidWorks. Then 6 of the 1 inch by 1/4 inch bolts are welded into the 3 holes on each side of the triangular plates in order to make them perpendicular to the face of the plate. The next step is to connect the 3 wheels to the 3 connecting rods using the 3/8 inch bolt, 2 washers, and a nut in the order as seen. The next step is to connect the wheel connecting rod assemblies to the base plate. The next step is to install the second triangular plate by aligning the bolts into the slots of each of the connecting rods and using the corresponding washers and nuts. The last piece of the assembly is the clevis pin as seen on top of the assembly and is installed after the assembly is put onto its axle. Lastly, the entire assembly is inserted into the axle and held in place by a cotter pin as you see inserted through the axle. Also, the clevis pin has been inserted, locking the wheels at their desired dimensions.
As you can see, the wheels are able to move farther apart and closer together as the front triangle is rotated. The 3 holes on the front plate line up with the single hole on the back plate. A pin is inserted through the front and back plate to lock the wheels in position. The holes could be spread further apart or moved closer together in the design to change the spacing of the wheels to the desired height. The data points represent the value of each position of the mechanism. A spline was created to find the distances between the wheels when rotating from the fully retracted position. This would be a good tool to determine where to add new positions if the device were to be improved. The blue line is the maximum stair height, which is measured from the edge of one wheel through its center to the center of another wheel. The red line is the minimum height, which is measured from the edge of one wheel through its center to the closest point on either of the 2 wheels.
Even though our design went through many revisions, there is still room for improvement. The first feature we would improve would be the bolts connecting the plates to the slots on the connecting rods. The idea is that these bolts can slide freely in the slots, allowing the mechanism to expand and contract. However, the threads create a lot of friction, not allowing a smooth action. To fix this, we believe either removing the threads from that part of the bolt in the shaft or using a non-hollow material should allow for a smoother action. The second thing we would like to change is specific to the manufacturing process. The Beverly shear used to cut the sheet steel caused a lot of bending and tearing of the metal, resulting in a lot of time spent grinding and bending back to be flat, which still resulted in a non-flat workpiece. To improve this, we believe that it would be better to cut these parts out using a metal bandsaw. The next thing that needs improvement are the welds connecting the bolts to the plates. This was done during the manufacturing process to add rigidity to the plates and bolts for a smoother action. However, the welds ended up not only creating more friction, but preventing the pieces from sitting together as they were intended. We believe this could be fixed by either welding bolts at the outside of the plates or just by having cleaner welds by someone who is more experienced and accurate with small welds. The final improvement we would like to make is the materials used. Most of the materials we used were recycled from the machine shop. The steel plates, while roughly 16 gauge, were not stiff enough and bent when the cart was pulled. The connecting rods were made from hollow aluminum tubes, which created friction with the threads in the slot. Either using solid tubes or filling in around the slot to make it a flat face would improve the action of this mechanism.